Now we will move on to the demonstration session by Mr. Manjil Situla. So Manjil, if you are there, you can take over and carry on.
Greetings, everyone. So thank you, Professor Tijas, for such an insightful talk on the passive scalars and how to model them using the different equations. So now we will be dealing with the example problems that Professor Tijas has presented in his talk. So we will be using the passive scalar to model and simulate the pressure stressors. So it is a non-reactive chemical species. So basically, passive scalar is any quantity that do not react with the flow or that do not influence the flow. So it is actually transported by the flow, but it do not influence or react with the flow. So that's the definition of the passive scalar. And basic outline of today's workshop would be like we will be modifying the uh, scalar transfer form solver to model our equations in of the passive scalars, and we'll be learning to how to set up that case and doing the post processing in ParaView. So basically, we'll be tweaking slightly the scalar transfer form solver to incorporate our equations in the solver. So you can call it like modified solver. So yeah, problem definition is that we will be setting up a case to model the passive scalars as tracers, and we'll be comparing the diffusive and non-diffusive scalars, and finally post-processing the results in ParaView. So okay, the equations were already presented by Professor Tiras in his lectures. So this is the equation that we will be modeling in our solver. That is the changes that is required in the scalar transfer solver. These equations will have to be incorporated in our solver. So and this is a basic transport equation. So S is the scalars and diffusivity is there are diffusivity constant, and SC is the source term. The source term basically means for the first order and for one single reactant, the source term would basically be minus Ks, depending upon the R is RA or RB. So if it is if scalar one is converted into scalar two, then scalar one would have in the negative, we will have a negative sign, where scalar two it is being produced, so it would have a positive sign. So these all the source term, basically we are modeling the source term in our solver. So K is the kinetic dead coefficient with as a unit per second, and lambda is the diffusion coefficient. So source terms has been modeled in the solver as per our problems, and we will learn how we will model how we will model these terms. So our first case would be setting up the steady state and transient case. So the first case that Professor Dheeraj has presented is the parabolic flow. The flow is parabolic, and that flow transports the scalar from the inlet to outlet. So first of all, we'll learn how to set up the case, uh, and then we'll discuss more on that after we run the cases and post process that in ParaView. And we'll be doing this entirely in steady state, because if we do in transient state, then it would take a longer time, because RTD resistance time distribution is to be done in the transient state to find the actual time, but we cannot do it now because this requires more time. So we will just run the steady state case, and I think it takes 3 times to 4 times the RTD average RTD time for the inlet flow to reach at the for all the inlet flow to reach at the outlet. So for 20 seconds, it will be very it will be a time consuming simulation. So we'll be dealing with the steady state cases, and I will show you the transient cases setup also, but you can run it on your own, and how the graphs would come out to be. I will show that, but we will be doing a steady state here as a hands-on today. So first of all, let me describe the geometrical domain. So it's generally cylinder with 0.5 meters length and 0.001 meters diameter. This is the and these are the boundaries. So it is basically a pipe. We can tell it as a file. Okay. Now I will be sharing you the template case. I think Ivan has shared in the chat. Okay, thank you, Ivan. So I will request you all to download that. So let me give some time for that and then copy paste in the run folder of OpenFOAM 9. So please all, so this is the template case. So just copy and paste it in the run folder of your OpenFOAM version 9. Okay, this I think this is the files that is inside the template case that I have sent you. So you can name S or S1, S2. That depends upon your that depends upon the user. So this is the temporal term and divergence term. So we don't have to change the phi term. So that's the OpenFOAM will calculate it on this on its own. That is the flux. But the necessary changes that need to be made is introduce the scalar, introduce this term. Like in this case, there was a uh, variable called temperature, but now we have scalar one. We have filled scalar one, not because this is according to our equation. So you could have named T. That would not make any difference. But for our understanding, so we have named it scalar one. Similarly, to for the Laplacian terms, we have used the diffusivity as ds1. So here you can see that there was a dt term, but now we have used ds1 because this is also for our understanding. And this is the scalar. So the this term, Laplacian term, how we are modeling this using. So if you take it to the right hand, left hand side, then it gets negative sign. And then this source term. Now for our problems, the source term will vary according to our problems, different example problems. So right now I'm using minus ks1 into scalar one. That is the scalar one is decaying, or that the scalar one is uh, converting to another term, or it is being consumed. So this source term says that. Okay, so basically, and what we need to do is in resolve the scalar one equation. So here it's the same thing. Just when we are tweaking some parts, so tweaking just the variable names. So it is the same. So this is how you can import that inbuilt solver in OpenFOAM, and how you can tweak it to match your problem or to formulate your equations. You don't have to understand so much of the C++ here. What are the yeah? Of course, you need to look what are the header files included, and if you go inside it, then there are many things to look at. But right now, our focus is just how we can implement that equation in our solver. So I think you have understood what how we have implemented that equation in our solver. So we need to solve for the scalar one, and this is how the solver is modified. The scalar transfer form is modified to new scalar transfer form.c. Okay, after you change in the source code, there are other changes as well to be made. Okay, now if you go to this to the template case, now you can see that there is another inside new scalar transfer form. There is another header file called createfields.h. So just open createfields.h. Now you can see that since I have introduced a new field with the name scalar1, so I must tell the compiler that I have introduced this field, so I must introduce it in the create fields.h. And this header file is being called in the .c file by include create fields.h. So you can see that we have called this header file as well in the CPP file. So what we have done now is we are introducing, since scalar one, what is the type of scalar? Is it a scalar? It is a vector. So you must know that, and you must write that if it's a vector, then volume vector field it should be. So in this case, we have just introduced the scalar one. So this is the addition that has to be made in the create fields.h. Now other rest, you do not need to change anything. Okay, and the next thing that you have to change is, here you have to also include the transport properties in the create fields.h. You can see that we have introduced two new transport properties, that is ds1 and ks1, and we must tell the code, or tell the compiler that we have introduced this, and we must define it in the create fields.h. So I have defined. So these, if you go to the original scalar transfer form, so if you go to the original scalar transfer form that is the available solver in OpenFOAM, and if you open at create fields.h, so you can see that instead of scalar 1, there is a volume scalar field T. So what you need to do is you just need to change the name here. Yeah, we have changed the name, and instead of dt, so you can see that it has a divisibility constant by the name dt. Now what we have is, we don't have that. We have ds1 and ks1, so we also introduce that in the create fields.h. Fine. So these are the changes that needs to be made. Okay. These are the two changes that I have made. Now the further change that is required is in the make file. So if you go to the new scalar transfer form and go inside the make file, there are two files actually, but the files just don't identifier options, just don't identify. It is the artifact of copying the file manually. So we have copied the file from another location to the round folder manually. So these files will get generated. You can just ignore them, or you can just delete them. Now another important thing to look at is, if you look at options, I guess. If you look at options, okay, these are the different libraries and the path to them, so that if because we have included different error files in the CPP file, that is, and we need to assign where these files are located. So the options file do that. We have provided the location of where all those files are located. And rather important than this, the other important is the files file. Now you can see that you have introduced, now what the name of the your source file. So we have new scalar transfer form.c. This is the the CPP file that we have created. So you need to assign the name here before compiling. So we have used the source file name, and another important thing is you need to change this. Okay, so let me show in the scalar transport form files. So you can see that the execution, where it is, where will, after we compile, where will the compiled code be saved? It will be saved in form app bin and by the name scalar transfer form. But we don't want to save it in the form app bin, because the form app bin is primarily for the OpenFOAM original solvers. So if you save it there, then that might create problem with the installation files. So you want to save it in the foam user app bin. You need to make that change also. So instead of foam app bin, you need to store, or you need to locate it in the foam user app bin by the name scalar transfer form. So after you compile this, then this will get saved in the foam user app bin. So $foam user app bin is the location. So dollar gives the location of the this is the variable, and this has some certain path, and this is saying that navigate to that path. Okay, so these are the required changes you need to make before you compile the code. After these changes are made, then good to compile the solver. Okay, now let's go to our Nishkaya transfer form. Okay, now open our terminal here. So just open the terminal. Okay, go to your run directory. So if you type run, then it will navigate directly to the run directory. Now inside the run directory, go to Nishkaya transfer form. Inside run, there is another folder called template case. Okay, inside the template case, there is another folder named by Nishkaya transfer form. So just go inside template case, and inside template case, go inside Nishkaya transfer form. Okay, I think you have opened the path in the terminal. Now we need to compile this. So first of all, before compiling, just clean it, wclean. So this is the command for cleaning. And after you clean, just type wmake. So after you type wmake, the wmake is actually whatever is written in the make file, it will execute that. That is like a script that will execute the contents of the make file. So wmake it will allow you to compile the solver. So after you do wmake, now your solver is ready to be used. Now where it will be saved is if you type form user, I think app bin. This is the command. Form user app bin. Let me see. Okay, so if you type cd form user app bin and list here and just type L list, you can see that your solvers that you have created, your modified solvers, it's present here. So just type cd dollar form user app bin, and if you tell L, that is to list the contents of that folder, and you can see that, and everything that you have new solvers that you have compiled, it will be located here. This is just for the information. Okay, let me go back to the run folder. I hope you have all compiled the code using wmake, and after you do the wmake command, so just to navigate to the new scalar transfer form where the contents of the solver is stored. So you cannot do wmake going at the template case. So just navigate to the new scalar transfer form folder first, and then hit the command wmake. And after that, if you type where are our compile codes stored, then so the compile source, the solvers are stored in form user bin because we have provided the location in the files, that is inside the make file. In the files, we have provided the location as form user bin and by the name new scalar transfer form. So if you just type cd dollar form user bin, then it will give you the location, and just type L, that will list all the contents of the folder. So after you do this, check if it is compiled or not. If it is compiled properly, then it should be present there. Okay, after you do that, now here.
Excuse me.
Yes, sir.
You have shown there are around some 10 files and folders inside this bin,
Yeah,
but
yeah.
I have only one.
Okay, actually, that is because I have compiled other solvers like manually. That is why it is located here. So
Okay, because I have
this,
only one called this new scalar transport.
yeah,
That's
and
all.
now yeah, it's only one because we have just compiled for one solver only. Now we
Okay,
will
okay, okay.
slowly do for the different solvers, 1s, 2s, and you'll know how it will be located there. Okay. After that, let's again navigate to our template case. Just type run. It will direct you to the run folder or run directory. And let's go inside cd. Cd will navigate with the navigation command. So it will forward you to the template case. Okay. Now let's discuss on the first case. So we have included this equation in our solver. So this part is done. Now let us now set up the case for the parabolic flow from the inlet. How we do that? So this and we will I will show how tangent and steady cases are done are set up, but I will only run the steady state case. Now another thing to notice is that if you can see here, then scalar in the new scalar transport form. So just you if you look at the solver, you can see that we have not solved for velocity, right? But we need the velocity to for the scalar to transport or to elevate, but we have not solved the velocity. So what do we do now? Because in our equation, so if you see our equation, then there is a term called velocity, but there is no mention of velocity in our equation. So how do we do that? So actually there is a phi command. There is a phi, which is the flux that is volumetric flux, and it requires u, that is the velocity. It requires velocity field, or it requires the velocity to be solved. But we are not solving velocity, so we need to provide velocity field. So how do we do that? So there, you can see that there is another folder called flow inside the template case. In the template case, you can see that there is a folder called flow. Now it is this part inside this part where we solve for velocity and copy the velocity field to our scalar case. So I'll show you how it is done. So I just want you to understand why it is done, because you can see that we are not solving velocity. Now we need to provide the velocity boundary condition, because you can see that in the scalar files there are two boundary conditions required, that is u and scalar 1. Now we need to provide the scalar we need to provide the boundary condition for u, but we are not solving for u, so we need to provide the field for the u. And we won't solve velocity here, we solve the velocity in the flow folder, in this folder. I think you understood what I mean to say. Now let's look at the boundary condition of the flow. So let's just get into the u. So just go into flow folder, and flow folder go inside 0, and inside 0 there is a file called u, that is boundary condition of velocity. Now this is the first case where we want parabolic flow at the inlet, right? So we use the coded boundary condition, coded fixed value boundary condition. So what we are doing is we are specifying our radius, we are specifying the maximum velocity. Our average velocity is 0.1 meter per second. So please be clear on that. And our Q max is 0.2 meter per second. So what we are doing is now we are specifying the jet velocity by this paraboloid for equation. So this is the equation of the paraboloid, and this 1 minus is done because it's an inverted paraboloid. So we are specifying at the inlet the parabolic shape at the inlet, right? So we are in the z direction. So you can see that at center, if you consider, if you imagine at the inlet at the center point where x equals 0, y equals 0, then for the parabolic profile, we need z to be u max. So if you see that if you use here y equals to 0, x equals to 0, then it would be u max. So at the center, that is at the center point, z is expected to be the highest velocity. And similarly, at the far end, that is at y equals to 0, or x equals to where y equals to the highest radius point, that is r is the radius. So since we have this r is the radius, so it is actually x by a plus y by b square, the equation of parabola, but a and b equals to r in our case. So that is why r is introduced here. And if you at the far end, you can see that umax z turns out to be 0. And if you want to understand what this code says, then it is saying that just this CF is asking for this face center of every patch. So you are going to the patch and it is asking for the face center. So this CF is coded inside the open form. What it does, it will automatically store the face center values. And what we are looping is, we are looping at every face, and we are finding the face center values. And after we find the face center values, we are assigning that the first coordinate to x and the second coordinate to y. So this is just the in the matrix how we assign. If in the simple coding, this 0 will represent the first column and the 1 will represent the second column. So 0, if you have x comma y, then 0 will represent x and y will be representing y, and we're assigning that to the scalar x, scalar y, and this is used in the in this equation. And these, after we solve for this value, and this will be assigned to the face center values, that is the field face I. So field represents a velocity field, because we are writing writing this code in the velocity boundary condition velocity file u file. So field will represent just the vector velocity vector field at the face centers. So I think you are clear on this. So what is this equation and why it is introduced here? This is because we want a parabolic profile at the inlet. So okay, so and the outlet we have zero gradient boundary condition, and at the wall we are using the no slip boundary condition, because we want the parabolic profile. Now, if we wait for the flow to fully develop and then develop itself as a parabolic profile, then that will take a longer time, and it will also take a longer pipe section. So we have introduced the parabolic velocity directly at the inlet by this boundary condition called coded fixed value. So this is important. So this is useful, very useful in such cases. So I just want you to understand the logic behind it rather than the syntax and this course, because this is available. You just need to understand the logic and how it is coded. Okay, after that, this is the let's see the pressure boundary condition. So it's the zero gradient boundary condition. So this is the same boundary condition that we have been using. So that there is not any important thing in this. So after that, let's see at the constant. So momentum transport. So if you go in the, we are doing for laminar case. So this is not important. This will not be executed. So just we are doing laminar case. And the transport properties, I think new value is required. So this is the new value. Transport model is Newtonian. So and the system file, now the system file, we can see that we have already learned how to make a pipe in block mesh. So I don't need to explain all the block mesh code. So this is the same code, same block mesh that is used to make a pipe or cylinder or a pipe. So all of you know this, so you can look it inside this. Okay. So now you can, in the control loop, now you can see that we are using a simple form solver, that is the steady state incompressible flow solver. So we will be for the flow simulation or for finding the velocity, we will be using simple form. So this is the steady state solver, and we'll be executing this start time 0 and because it's a steady state, delta t is just it has no physical meaning here. So start time will be 0 and end time will be 50. And then we'll writing right interval and all these things. And there is important, I think, pause write. Yeah, pause write means that we want to store only the last file. So now we are running for 50 seconds, right? So it will store file at 10, 20, 30, 40, and 50 seconds. That is, it will store say 5 files up to 50 seconds. But we don't want if we don't want all that files, all the time steps, data, then you can just write 1, then this will only store the latest file, latest time step data. So this is also handy. It also will be handy in because this will occupy less space, and if only the last time step data is data is required, then we can use this first write command. Okay. So there have schemes file, every solution file. So these are the solution controls and numerical schemes that is used in simple form. So we have already known how these schemes work and how we set up the algorithms, solution control. So in the simple form, if you go at the simple form, then you can see that these are the how you solve for the the solver that is resolving the pressure field. So these are solvers that we have assigned, and the same in simple form, the selection factors will also impact the convergence of the solution. So see, you can see that 0.9 is more stable, but 0.95 is more convergent. So if you increase the value to a higher value, then that would slow down the simulation because it is multiplying the difference of the new. So this is it actually 0.95 will be more slow, but it will be more convergent. So these are the less. So you can play around with the lesson factors in your cases. If your simulation is slowing down, or if your simulation is diverging, then you can just what we can do is we can increase this number. Okay, these are the solution controls. So now I think we are ready to run the simulation of our flow case. So let's go inside let's go back to terminal and get inside the flow. So just navigate to the flow folder, cd flow, and there is an all-learn script there. You can check the all-learn script, what is there written. So first, the all-learn script will execute the block mesh command because we need to make our mesh. Then we are running the simulation in parallel. So we need to decompose our case. So we are doing it using 6 processes. So you can see that in the decompose part, I have assigned the number of subdomains at 6, and it is the scotch. The scotch method will automatically divide the domain into number of processes. So we don't have to do it manually. So scotch method does that.
Is Scotch the partitioning algorithm?
Yeah.
What are the other partitioning that algorithm available?
So there are many like simple algorithm, hierarchical algorithm, and we have. So you can check out what are the algorithms. So basically simple, scotch, and hierarchical. That 3 comes to my mind just now.
Okay, thank you.
Yeah, you can check it. So if you see the algorithms, if I want to show you. So if you just type user guide, then you can see that there are different algorithms. There are different. So this is simple, hierarchical, metis. So right now we are using scotch.
Yeah, Metis is available. Yeah, thank you.
Yeah. Okay. So let's go back to terminal and then execute dot / all run. This now we are solving for the velocity field. We're saying permission denied. So just type chmod plus x and all. So just type this. And that's it. Dot / all run. I think as of now, we will be doing these
Excuse me,
cases
after chmod plus x, what is that?
plus x space all and asterisk.
Excuse me.
Yeah, see, I will show you. So this is the command.
Thank you.
So I think as for the time limitation, we will be doing case 1, case 2, case 3, case 4, case 5, case 6, and case 7, and these case 8 and case 9 will be sort of for you to work or try the cases. That is the scalar 2, that is scalar 1 injected at the upper half, scalar 2 injected at the lower half, and at the interface there is a
CH,
reaction. Yeah.
CH mode, then space plus X, then space all.
Yeah. Asterisk, what we call, yeah, asterisk
All
sign.
star, but it is showing no such directory or file.
So you need to go inside the flow folder. Have you navigated the flow folder?
Okay. I'm sorry. So
Okay, just I think simulation is running. Okay, it has completed. So now we can see that the latest time data is being written. So if you go to the folder, then you can see that only the 50 latest time step data is written, 50 iteration data. So just now what you need to do is you can see that you have a velocity field generated. So what we want to do is now we want to copy paste this U file. Just press Ctrl C. Or you can copy this, and then you need to put it inside the scalar file. So go to the scalar steady case. We are running steady case, so just input it inside the steady case. So inside scalar steady, navigate to 0 folder, and then paste here.
Sir,
Yeah.
can you repeat it again a little slow?
Okay. So after the flow field is solved, so inside the flow folder, you can see that there is a 50 folder generated. So inside the 50 folder, you go inside the 50 folder, and then, okay, if there are 6 slots, if you don't have 6 slots, then just reduce the number of.
Excuse me, I don't have a 50 folder.
I think the simulation is running. Yeah, has it completed? Can you check it?
What was the command you gave after all run?
/all run.
I'm
This was the command.
getting
/all run.
foam warning like yesterday.
sir, in my case, it is showing foam warning, and in last, no time selected.
Same warning it's showing again.
So that you have got the error called floating point exception or something like that?
No, only warning. It's showing.
How many number of cores do you have in your system? So if you have less number of cores, then you need to change this while running in parallel. So you just try with 4 number of cores. Go to the system, inside the flow folder, go to system, and in the decompose particle, inside the flow folder,
In the flow.
inside the system,
Okay.
you need to go inside decompose particle, and then reduce the number of cores here.
Decompose part. Okay, good.
Reduce number of cores. How many cores?
Okay, it is. Okay. 6. What should I change to?
You can change it to 4 number of 4. If you have 4 cores, then change it to 4, or you can change it to 2. But the simulation will slow
4.
down. Yeah. And after you make change there, you need also change the all run command. If you go to all run command, all run script, and we have assigned 6 processors here. So you need to change it to 4 or 2, depending upon your processors.
Okay. In the decompose part dict, if I have changed it to 4, then here also it will 4,
Yeah.
right?
Yeah.
Excuse me.
Yes.
When I tried this all run, it said permission denied.
Yes. You need to type /mod +x this command first, and then /all run. Okay, you try to run. So run this case. I will show how to set up the case for the scalar.
So, excuse me, only two places we have to change the course.
Yes, yes,
Okay.
yes. Only in the decompose partict to assign the number of processes, and then in the all run file. So this is because we are running this case in parallel. So this is that is why we need to assign number of processes. So if you are just running serial, then you don't have to do this MPI run. Just you can type simple form. You can just input that command simple form. Okay, after that you will have the 50 generator 50 folder. So you just copy the U file from that control. You just copy the U file and paste it inside the scalar steady inside 0. So I've already copied. I won't have to recopy this. So because now we need something to transport our scalar. Now this velocity, now we have the velocity field, and this velocity, according to this velocity field, the scalar will be advected. So that is why we need to input, we need to solve for the U and put it inside here.
Could you please repeat whatever you did just now? Copying part?
So from the flow folder, from the 50, so if you have run the simulation, then there will be a folder called 50. If the simulation is complete.
Okay. Yeah.
Okay. Yeah. Inside that, there is a U file. Copy the U file.
Okay.
Copy the U file. And paste it inside Scalar Steady. So go back, go to Scalar Steady folder.
Okay.
Inside the 0, you need to paste it here.
Okay.
Okay. So after this is done, now let us see what are the bound conditions that we have used for scalar 1. So right now we are injecting scalar 1 from the inlet, and its uniform concentration with 1. So you have normalized it to a non-dimensional value. It is 1 or either 0. So we have in the inlet we are injecting uniform 1 with the concentration 1. And outlet is 0 gradient. It will calculate itself based on the nearby cells, and its wall is 0 gradient. 0 gradient means it will calculate the values based on the adjacent cell next to it, adjacent cells. So these we need to input this. So because now we are injecting from the whole inlet for the first case, we are not doing it from the half inlet. The first case was from the whole inlet, so we are for the whole inlet we are specifying the value as uniform 1. Okay, this was the scalar 1 boundary condition. The block mesh file is same. The control dict, you can see that there are some changes. So now we can see that the application that we have used is the modified solver that we have just compiled, that is new scalar transfer form. So this is the important part that you need to change or you need to consider. And after that, what are the things that you need to add? So you can, if you go to FV schemes, now you can see that right now this and this you can just comment out, or you can just leave it as it is, because we don't have scalar 2 and scalar 3 files. So we can see that we have changed the divergence of in the previous cases we had divergence of phi comma u. Now what we are solving for scalar 1, so we need to change this also scalar 1. Similarly in the Laplacian schemes, change it to scalar 1. You don't need to change. There is I have already made the changes, so it is available there. Just this is just with information, and we are doing a steady state case. So you have to mention steady state here. So rest is same. Now similarly for the happy solution. For the happy solution, now we can see that we need to solve scalar 1 or scalar 2 or scalar 3. We'll solve it in the other cases, next cases. And what solver we have used? This is the solver. And yeah, depending upon your field, so you need to make additional changes in FV schemes and FV solutions also. Now residuals also similarly. So just you can just take one tutorial for reference, and what you need to make changes. Just you can change the name of that that you have introduced in your solvers.
One
Yeah.
thing is, even after changing that from 6 to 4, that was happening the same thing. Again, I changed that to 2, but the same thing, that is 5 time related problem was showing. No time selected.
Have you changed in the all run also?
Yes, yes.
What is the problem? What is the error message?
Error message coming, the last form warning, then from function int main int char star
Can you-
in file
Can you please
reconstruct.
paste it in? Not above that there might be some other error messages.
Okay,
Above
I'm
that,
pasting it.
above that there might be some other error messages also. Okay, yes, you can just run a simple form instead of doing it in parallel. That would work. So as of now, you just change. Just don't do it in parallel. Just run in serial. So delete this and just run simple form if the problem is occurring.
Okay.
Sir, should we change the number again before running simple form?
No, that will not look at the decomposed particle now because we are just running in serial. So you just did not change anything here. Okay, so after the simulation of the flow is complete and you have made changes in this, now we need to run the second case. So I think we need to hurry up a little bit because there are many cases that I need to show.
So while changing that in the all run simple form, what should I do with the decomposed particle?
Decomposed particle, it won't reference to that file. Okay, now after you have copied the U in the Scalar study, now we need to run that case. Scalar study. Now again, you can see that there is a all-round file. Now it's the same thing. If you are having problems with the decomposed particle, that might be because the number of processors in your system might be lesser. So it might be 2 cores or 4 cores, but sometimes you cannot use the maximum number of cores. So if you have 2 cores, then you cannot use the maximum 2 cores. You need to do it 1 core. So that might cause problems sometimes. So if you have 4 cores, then specify it as number of 3 cores as 3. So you can do that and try. Just don't put the maximum number. Just you do it with lesser. It's like one number less than that. If that does not work again, then you run this simulation in series, but this will take some more time. Okay, after you have done all these all the setups, now you need to run the case again. Just type /. So it is giving. Yeah, somebody pasted case is already decomposed with 6 domains. Use the force option. So just you delete that number of processes. So you can just type form clean tutorials. It will delete you can type form, or you can delete it manually. Clean tutorials. This will delete it manually. This will delete it automatically, form tutorials. Or you can also do both will work for this. So do this and then run the case. Now it will run because already if you had used 6 number of processors, then it was decomposed into 6 number of processors, and you change it to 4. But it didn't run because it was already decomposed into 6 processors. So just delete it, and then you can now specify number number of processors as 4 and then try it, it will run. So who was facing the issue with 4 number of processors? So you just run form tutorials first and then now change it to number of processors to 4 and then try it. After that, just do all run. So before running this case of Scalar study, so make sure that you just run with the number of processors as 4. If you have limited number of processors, then just run it with the number of processors as 4. Make changes in decompose predict as 4 and in the all run also as 4. Now in the next case. So in the Scalar study case, before running all run, make changes in these two files. In the all run, make it to number of processors 4. Specify as 4, and then in the system decompose predict, you change it to 4. Those who are not facing the issues, you can just run it with 6 processors. But if anyone who is facing that issue, then you can change it to number of processors 4. That will work. So we can see that the next simulation is also running. That is of this study case. Okay, at the meantime, I will show you our transient case setup. So this is for the Scalar folder is for transient case. So just the difference is in the FV schemes. In the FV schemes, you can notice that previously it was steady state, and now we have used Euler scheme. That is a transient scheme. These changes has been made in the transient case, and the solver use is same. That is, we are using the scalar Newton transform. And there is also one important thing to discuss. So in the scalar study, if you go inside the scalar study, if you go inside constant and you go inside transfer properties, so now we can see that there are these two these are two transfer properties that we have declared in our code. That is DS1 and KS1. This KS1 is the kinetic rate coefficient, and DS1 is the diffusivity coefficient. So we can see that we have assigned it 0 as of the first case, because in the first case we are not involving any reaction. Just in the first case, you can see that. Okay, this is the first case. You can see that we are injecting the scalar from the inlet, from full inlet, and the scalar is moving towards the outlet. There is no any conversion, or there is no any reaction going on. This is the unreactive case. So that's why we have specified it as 0. Both the values are 0. So you can see that our case has been complete. So let's try to reconstruct this. I think we can run also post process in parallel itself. Okay, so the reconstruct part command was missing here, so it didn't reconstruct automatically. So you can reconstruct it, but I think this will take time. So let's see. So after your simulation is complete, so just I will reconstruct part. This is the command.
Yeah. One question. Last time when you copied the U file, you didn't reconstruct it. Now you're reconstructing it. Why?
Because I just said that in all run file in this second case, the reconstruct file part is missing here. You can see that I have not included here. So you can just include here and then run it to reconstruct. So let's do reconstruct. Actually, we can visualize the result or post process the result in decomposed state also. but doing it in the reconstruct register, it would be quite fast. So after you do reconstruct part, now let's do the post processing. So just open paraform built-in. So here run this command paraform built-in. After you reconstruct, if anybody is slow or if you are stuck in something, then I think we can discuss it later, because according to our time, we need to cover many things here. So I'm going a bit faster. Now, if after you open paraform, after the simulations are complete, then just open paraform built-in, then just do apply. Okay, this is our domain. Okay, now let's slice this domain, because we want to see the inside of it. So just go into the slice command. So here is a command called slice. So you can see that just above the pipeline browser, there is a command, there is a filter called slice. So just click here. Now, in which plane do you want to slice it? So actually, we are doing it in the X normal direction. So in the YZ, we want to see YZ plane. So you can see any plane here, because it's a parabola, and if you cut it, it will always be a parabola in any plane. So if you do it, then click apply. So just hide this plane. There is an option called show plane. Just you untick it and it will hide the plane. Now you click apply. Now you can see that we have reduced it to a single plane. Reduce the domain to a single plane. And if you do the drop down menu, then if there is scalar 1, if this is missing in yours, then always make sure that you tick these cell arrays, these two variables, u and scalar 1. So let's see scalar 1.
Sir, after selecting or clicking on the icon of slice, then we need to select the plane also.
After you select slice, then it will select type. Slice type would be plane.
Yes, but which plane I have to select?
Just so you do wait. There is option called X normal. You can try any of these: X normal, Y normal, or Z normal.
Which position it will be? Location?
It would be at the center. At the center of
Okay.
this.
Okay, only center. Origin,
Yeah.
from the origin. Okay.
Yeah, so it would look like this plane.
Which plane?
Any plane that is passing from the center line of
With
the.
the red line, that is the
Yeah.
plane.
You just type slice, then it will automatically give you this plane. You don't have to change any coordinates. I think there. Just type slice and press apply.
Okay.
In the variables, there are two U's. Why there are two U's?
This is actually the point data and the area data. So these are two different data. It will help you that this is of the whole area or the volume, and this is for the point data. So, but you just need to select the point data. We are looking at the data at the center point of the cells, not the cell data. I think the area data. I guess so. I'm not quite sure on that, but
Thank you.
okay. Now, so you can see that the scalar as so you see that because we are doing steady state, so you cannot actually visualize every time step data. So how is the flow moving in the domain? So if you do it in transient state, then you can see that the first how the flow will be a parabolic. The scalar will move as a parabolic shape and all that. So right now you can see that we don't have enough. So if you customize it to 0 and 1,
Sir,
so
one
you can.
problem related to the calculation solving. It is calculated up to time 50. It is showing, but still at the end it is showing the same warning, foam warning. I do not know whether this warning can be avoided. Means it should be overlooked.
Have
It
you
is
add the
calculated.
yes run altogether?
It has
Yeah,
calculated. 50 folder is created, but
yeah.
still at the end the warning is coming.
Okay. Right now you can ignore that warning if it is not an error. So if it's error message, then we need to consider it. But it's warning, so just ignore it for now.
Okay. Thank you.
So actually, if you run the case in transient, so what you can see is at different time you can see that it's you can expect it the parabolic profile. So even though we have mentioned here the parabolic profile, so we actually in the post processing we are not able to visualize it clearly. So if you run the case in transient, then this will then you can see at different time steps data, and you can see that it is parabolic in nature, as I have just showed you here. So this is the case. Okay, so now let's learn to plot the like post process the equation of the cup average concentration. How do we do that? So you can see that the flow has not reached the outlet yet in 150 seconds. So if you got the last time step, then you can see that the flow has covered from the inlet to outlet. So now what you do is extract. You need to find the curb average concentration at the outlet, because we can collect the sample from there. But if you want to do inside this domain at different cross sections, then you just do the area average area average. You can take the area average concentration, but you can take the volumetric average at the outlet. So after you go to the scalar steady form, and then you go to filters and alphabetical and select extract block. There is a filter called extract block. Just select extract block. So before selecting extract block, again go to the scalar steady form in the paraview scalar steady form, and there is and if you go down in the properties window, so you can see that what do you want to show here. So we want to extract the outlet, so we need to select the outlet also from these mesh regions. Just click on outlet. In order to extract the outlet, you need to first go to scalarstudy.form, and then you need to select in the mesh regions, you need to select outlet, then click on apply. After that, if you go to after you extract the block, then there will be an option available for outlet. So right after you do this, and only this option will be available to extract the outlet. Otherwise, you won't see the patch called outlet. So you do this, you click on apply. So now we have see that we have the outlet block extracted. If you go to scalar, so you can see that the scalar has completely reached the outlet. Now I will teach how to do this. So here you can see that how to this is the equation for the COP average concentration or the volumetric average. And how do we do this? How do we post-process these S average in ParaView? So right now, are you all up to this point, or you are lagging behind this? At which point are you all? Can you anybody say, like, if you have if you are following me up till now, or you are stuck behind this? You can unmute and say that.
Yeah, I have reached this point, but the contour is not full. I mean, the outlet, I am getting only velocity profile.
Okay, so you need to check it from here. Go to cell areas and then select U and scalar one. Both the you can see in the left hand side the properties window. In the cell areas, just check both the U and scalar one.
Okay.
Okay, if you all have reached to this point, then now we can move on with how to plot the COP average concentration. How to calculate the COP average concentration using the inbuilt features of ParaView. So let me wait for 2 minutes. If you have any queries till now, or if you are stuck in somewhere, then please let me know. If not, then I will proceed with the concentration. So now you can always have the recording of this. So I will be demonstrating how to do this as of now. Okay, now we want to plot this concentration, COP average concentration. So you can see the formula down here. Is integration of U times S over the area divided by U average into area of outlet. Now what we do is, now just there is a filter called calculator available. So after you extract the block, there is a filter called calculator. Just click on calculator. Now in the calculator, there is an option where you can input so you can just rename it as the numerator. Just using numerator, and then what is the equation is, we need to multiply U times S. So just click on scalar 1, and then multiply it with vector U. Right, this is according to equation U into S. After you do this, just click apply. Now after you click apply, now what the next thing is needed is you need to integrate that over the area. So there is also a filter called integration available in ParaView. So if you go to alphabetical and you go to integrate variables, there is a option, there is a filter called integrate variables. So you can see there integrate variables. So just click on integrate variables and click apply to integrate over the area. So you can see that we have in the X, Y, and Z direction. So right now our Z direction is important because the flow is the scalar is flowing in the Z direction. So we will take this value, that is the Z value, and then what is the next case? We need to divide it by U average into area of outlet. So what we do now is, again open the calculator. Now what we want to do? We want to divide the numerator, the Z part of numerator, by U average. So our U average is 0.1 meter per second. And if you do the area of the outlet, then it's pi r square. And pi r square, if you do this, the diameter comes out to be, the area comes out to be 7.85. So our diameter is 0.01 meter. So it comes out to be 7.85 e minus 5. If you do this, now you can rename this as S average. Now click on apply. So I think you can second point. Let me see the area. Pi into okay, this is the area, and our velocity is 0.5. So you can see there in the calculator part, the is actually the S average should be actually 1, but we can see that there is a slightly greater value. That this might be, it must be actually a slightly lower value, because it will asymptotically reach the average, the inlet concentration. So this might be due to the numerical diffusions and the air in our simulations. So these actually this should be 0.99 and it will reach asymptotically. So if I show you the graph, then it would look something like this. So you can see that this is a transient case. So you can see that after 2.5 seconds, the flow will reach the outlet. So this is the average concentration at the outlet. So you can see that the flow will reach the outlet and asymptotically reach the inlet concentration, because the flow at the walls will reach slower. At the walls are slower, so that will reduce the concentration. So in this way you can plot the S average concentration, that is the copper average concentration. So after that, let's move on to the next case. Now you can do for the flat velocity profile. This is the same. You just need to instead of during the coded fixed value in the flow, so you can change just this boundary condition at the flow folder. So instead of doing doing the coded fixed value, you can just type fixed value and uniform what we want, the velocity 0.1 meter per second. So that you can do it. So you don't have to do the parabolic velocity, just you can input the value 0.1 meter per second. So that will do it in the flat velocity profile. And the flat velocity profile, it will be a step input. So you can see that because the flow will reach the outlet at the same time, that is, it is not a parabolic profile. So you can see that at the 5 second, near to the 5 second, not exactly 5 second, near to 5 second, because this is also some problem of numerical diffusion. And at 5 second, you can see that the flow has reached inlet concentration of 1. Instead of going asymptotically, it is like a step input, because the flow will reach the outlet at the same time in the flat velocity profile. So another thing you can see is, so let me show here. So let's go to extract block. So let me also show you the inlet part. Okay, so I think I'll show in the next case. So I think you have you have now idea of how to calculate this in the paraview. So let's now move on to the third case. Second case is the same as the first case, just you need to change the velocity profile as flat velocity profile. Instead of doing the coded fixed value, you can change it to 0.1 meter per second in the Z direction. Now the third case is half hour injection with no diffusion. So now we want to inject only at the uppermost part of the inlet. So you need to what we need to change is, so if you go to the scalar folder, then in the 0 folder, in the scalar 1, so you can see that there is another boundary condition called the coded fixed value. So you can see that for r greater than 0, we have assigned as 1, and for r less than 0, we have assigned as 0. So this is the boundary condition that we need to apply for the half bore case. So just press Ctrl C. Now let's create a new folder called half bore. And then let's copy the case 0 0 constant, the required case, the required original setup in the half bore. So now what I need to change is in the 0 folder, in the scalar 1, I need to replace this inlet boundary condition, because we are now injecting in only the upper half, and in the lower half we want it to be 0. This is the case. So this change has to be made. Now we can run the case. So if you go into the half, now you don't have to solve for velocity again, because we have already solved the velocity in this case. So you just can copy this and then paste it here, and then paste it inside here, inside the scalar steady case, inside 0. So in the half bore case, in the 0, you can just copy paste here. So now you can run the case. The case is set up. The scalar will be only injected in the upper half, and in the lower half, the scalar will be 0. So this is the case setup for the second case half bore. Now I won't run the simulation. I will just show how you can set up the case. Now let's look at the next case. Now with diffusion and without diffusion. Now you can set the diffusion value at the constant. So inside the constant there is a folder file for transfer properties. So now without diffusion it would be 0. That's the case. It will be 0 without, and there is no reaction involved here. So KS1 will also be 0. Now with diffusion, what you need to change this value. So if I create a new folder, half bore diffusion. Now what I need to do is just copy this here, and in the transfer properties you need to assign the value for the DS1 diffusivity constant. So right now, according to our trial value, so this works fine, 1e minus 5. So I could have showed you, I will show you the without diffusion and with diffusion case just now. So I have run the simulation in my system already. So let me just show you how what are the results. Versus cases. So these are the cases. Okay. So this is the run case. So let me just show you in parallel. Okay, let me check the mesh regions, outlet and inlet both. Okay, now let me extract a block. Now let me extract both inlet and outlet. Let's start with the edges. Let me see scalar 1. Scalar 1. This is at the outlet at 150 at the it does not yet reach the outlet. So let me just show you at the inlet part. Let's plus it. So now you can see that this is the inlet where we are injecting the scalar. The scalar is only injected in the upper half, and the lower half the concentration is 0. So you can see you can customize it, the color map here by selecting 0 and 1. Now you can see at the center line, there is a slight, because we have in our code, we have said that for r greater than 0, just this you can just equal to, so r greater than 0, you just assign a field as 1, that is the scalar as 1, and just r less than 0 at 0. But near the center line, we can see that there is a slight band here. So what is it happening is due to the mesh, coarse mesh and numerical diffusion. So we can see that we have assigned the center value just above the center line. So just above the center line, we have in the center, in the first face above the center line, in the cell center, we have the value of scalar as 1. And in the lower value, in the lower cell, there is a scalar value called 0 in the lower cell, just above below the center line. So now in between these, there is a sharp difference, 0 and 1. So you need to interpolate in other parts. So while interpolating, then this will interpolate between these 0 and 1 values, and we can see that there is a slight intermediate concentration at these bands. So more the coarse, if you have a more coarse mesh, you can see that at the near the arc, you can see that the band, the mesh is more coarse, and the band is again greater. In the center part, the mesh is less coarse than at the outer part, so the band is quite smaller. So this is an artifact of coarser mesh and numerical schemes. So this is numerical diffusion. So now this is the case. So you can plot the scalar concentration in the same way. Okay, I'll plot this at the outlet. So I think I will have no more time on plotting this. So you can plot these value, and you can run the next simulation. So you can run the next simulation with the diffusion case. So this is the diffusion. So this next case is the diffusion case. So this is half-board d nu. So what I've done is I have in the constant transport properties, I have included the value as 1 minus 6. So this, you can use this as ideal value. You can run it on your case. So what we can observe is, now let me So I will show you at the outlet what is happening at the outlet. So this is at the outlet. So I have extracted all in the outlet part. Now this is without diffusion. Now let's just see with diffusion what is the difference. So as in the regular way, let's just select outlet and then extract the block. I think this will be the last case I will be showing you. So other cases, I will provide you the files, so you can check that files and how it is implemented in the source codes. All things you can check it. So now you can see that there is a difference. The scalar has moved to the lower part also. So if you plot, so you can see without diffusion, the scalar is mostly present in the and it is uniform distributed. But you can see that there is radial diffusion we have induced in the second case. You can see that the scalar diffusion is quite different in different parts, because that is due to diffusion, the radial diffusion. And also, if you plot the concentration at the upper half of these two parts, so if you just plot the concentration on the upper half part, so in order to extract the upper half part, there is an option called clip. So you can just clip it in the what is the direction, Y normal, and then click apply. This is the lower half, so you can do it in the upper half. So in this part, for both cases, if you do for the upper half or for the both cases, you can see that in the second case, with diffusion, the copper base concentration comes to be lower than that of the without diffusion case, because the scalar has now diffused to the lower half also, and that is why this copper base concentration comes out to be lower than the without diffusion case. So this is what you can do, and you can look at the values by plotting the calculating the concentration. So that is it. So this we have covered mostly the third and fourth part, but the reaction part, the batch reactor, I think due to time limitation, we are not able to cover this, but I will show you the source code, what we do in the source code for the batch reactor. So for the batch reactor, we have implemented a new scalar transfer form, a new solver called Newton1s. So if you go at this case, so okay, so in the batch reactor, what you do is you just specify the coefficient value. So batch reactor, if you go at constant transfer properties, and you can see that I've now assigned the kinetic coefficient value as 1. So this is the solver that the reaction is taking place. The scalar needs to be decayed or needs to be consumed. So this is what you need to change the batch reactor. So if you look at the batch reactor, what you get is I think if I run the case, so the case is isn't run right now. Okay, I have run the case. So this will be the last case I will be demonstrating now in ParaView. So I think just wait for 5 more minutes. Okay, I wanted to show this case, but I think we need to end it here. So you can run the case. So in the batch reactor, we are just we can see that our solver is working fine, because if you set it to value of 1, then we get some plot like this. So this is our domain. We are just taking a single mesh, and what we can get is we will get a curve like this. So according to our time, so the scalar will reduce according to our equation. So in the next workshop, we will be dealing with the reaction mechanisms and all the equations. So please be connected so we can continue with these test example problems. So as of now, for this workshop, I think I will end up with this talks.
Okay. Thank you so much.